3 is, there's a lot in it, and I'm going to rush through a lot, and trust me that I spent more time on this stuff in the previous section. Going through, we run a prestige model, predicting prestige from education log to income and women. How do we visualize the fit? We fit the fitted values, which just means the y-hats, the predicted values, against the true values of the outcome. A better model, you'll see like this more resembling a straight line. A worse model, you'll see more noise in this data. Check the hints document for more explanations of this stuff. The leverage plots are pretty useful in terms of assessing, like, if you might need to rethink your model, if you might have some non-linearities. No, actually, that's not true. These are just the unique relationships between the variables accounting for the other two. Thank you. The residual plots are what I was trying to talk about, which can sort of give you hints as to whether there are unaccounted for non-linearities. They can also sort of show you if you might need to worry about heteroscedasticity, which I explain more in the last section. Basically means, are the residuals sort of more variable at some levels of the fitted values compared to others. This stuff, it does come up in exercise 3, but I think it should be relatively easy to read the hints document, get a quick understanding of what these plots are telling you about a model, and then apply them to the model that we do in exercise 3. Because it basically just asks you, run leverage plots, run residual plots, tell me what you see. So you just have to kind of have a rough understanding of what these plots show, run them on a new model, and describe if they're showing you anything interesting or not. Plot gives you a bunch of different plots. Residuals against fitted values, again, you would check for heteroscedasticity with that. The normal QQ plot, this is kind of, are my residuals normally distributed? Because this is an assumption that we make in linear model. If your residuals are very non-normal, that can lead to problems with your standard errors and your p-values and your statistical inferences. Again, standardized residuals against fitted values, residuals versus leverage. This stuff I go through in the hints document, so check that out. Okay, so contrasts. Contrast is just going to show you how you would dummy code a variable. So like I said, blue collar would be our reference level with prestige type, and we would have a dummy for prof and a dummy for white collar. We already did this. So this is just, contrasts is just another name for specific ways of converting categorical variables into numeric variables so we can use them in a model. I mean, contrasts, there's different kinds of contrasts. They're not all dummy variables. I think dummy coding is all we really do in this course, though. So contrasts, this shows that, yeah, question?
How would you change the reference in import contrast?
Yeah, good question. So like we can relevel with a command called relevel. So you can go relevel, prestige type, and then you go reference equals, say, white color. And then if I do the contrast, you see, no, it hasn't changed anything. Oh no, I didn't save it. So you want to like actually resave the variable with a new reference level. And then you can see white collar has become the reference level. But I'm going to change it back to blue color just so everything goes as planned. So with mean values, this just shows you the means of prestige for each of those categories. And now if we run the model, you can see that, like we figured out just now, the intercept of the model is 35.527. And we also just saw that the mean of blue collar, so the mean of the reference category, is 35.527. And you can also see that the slopes from the model represent the differences in means between blue collar and those other categories. So we get a slope, so a B1 of 6.716. This means that the white collar mean, A plus B1, 35 plus 6, it's about, what, 42? There it is. And the prof is about, 30 points higher. And so we get this slope close to 30. So it's a slope in exactly the same sense as any other slope, predicted change in y for a 1 unit change in x. But just with dummies, it has a specific interpretation as being a group mean difference. And this essentially is the key to understanding how we fit models with categorical variables. Convert them into columns with zeros and ones, and just feed that into the model, and just interpret the slopes. Remember. So this is question.
Just to make sure I understood it right, so if we were to put the professional as a reference, the other slopes would be negative, right? Just want to.
Yes, exactly right. Because the other means are lower. So it'd have to be, so A would be super big, and then you'd multiply the dummies by some negative value to get down to those group means. Yep, good question. So this is just another example. I'm going to just hurry through it. It's just a different data set. This is just showing you those group means for these three groups, 41. So this should end up being our intercept, I guess. We create a plot for the three different groups. We run the model, and you can see 41.045. Yeah, the reference group mean, again, is the intercept. And this is just some code for changing the reference group level. I'm not a fan of the update command in general. Like if I want to fit a different model, I'll almost always just fit a new LM with, the changes that I want to make to the model. Because it's not difficult, right? Like you can copy and paste your whole thing. We're not really saving time by using update. And I think it just is complicated, and it's just like another function you have to memorize and understand how it works and stuff like that. So if I was you, I wouldn't use it too much. Frederick likes it, maybe you like it. Each to their own, Coding is like a very individual thing. Okay. So LM can also deal with a mixture of factors and numerical predictors. So this is called ANCOVA, or ANCOVA, I call it, analysis of covariance. So in the first example, we're not going to have any interactions. Great. So this on line 98 is going to create a scatterplot matrix, but what it's going to do, it's going to create a scatterplot matrix with these variables, but divide the data by type. So like without this bar type line, it just shows you the bivariate relationships between all these pairs of variables. When we have this line, you can see that it's now kind of splitting the data up by a group and showing you, maybe you would look at this and see, it looks like there's some kind of interaction going on there. There's different relationships between these two variables based on group, based on type, blue collar, white collar. Yeah, that's all that's doing. You might need that in an exam though, so it's good to like make a note, remember where it is, remember this bar type command because you might need to do that. Okay, so now we're doing a model that includes type and excludes the percent of women. So we update the model and we take out the women variable and we add type. And then we look at it and it gives us these slopes. So they have the exact same interpretation as each other. They're all the predicted change in y for a 1 unit change in x. But what this now means is, so before, when we did not have education and income in the model, there was a huge difference, huge slope on prof, right? It was like 30 extra prestige points. But now that we have education and income in the model, the slope on prof has gone down, 6.75. Actually, it's no longer significant. How would you interpret that? What does that mean to you when you see that? You were first.
So not all the difference in prestige is explained by like the type of job you have. Usually education accounts for most of it.
Yeah, yeah. Yeah, like I would say that's a pretty good explanation. It's like we're almost treating like type type as affecting prestige. But obviously it's not just the words that we like, it's not just because we call a profession something that give it prestige. There's reasons we call something like professional, and they're related to income, and they're related to education. So here, you could say that income and education are kind of confounds of this relationship, and that like once you basically take away the relationship between income and education from prestige, what we call a profession doesn't really matter, right? Because what we call a profession is really related to the income and education of the profession. This is how I would interpret this. And like literally the model here kind of shows this as well, because we've got, so y equals the intercept plus there's a slope on income, there's a slope on education, there's a slope on white collar, and there's a slope on prof, right? So if I change prof here from 0 to 1, right, I haven't changed education. I haven't changed income, right? But like, so what my model is telling me is that, okay, like for a given level of income, if you don't change income and you don't change education and all you do is change the label, there's not so much of a change in prestige, right? Whereas before, when we didn't have those guys, we were not holding them constant. So like a 1 unit change in profession, not holding constant income and education, led to a very large change in prestige, right? So when you put other variables in the model, your interpretation of the slopes changes, right? So whereas before it was just kind of giving you this overall difference in means, now it's like, okay, well, if we're now thinking about two professions with equal income and equal education, what is the effect of changing? How much does it matter for prestige if I change the prof dummy, right? And it doesn't matter much, because the effect of type is largely explained here by income and education. Any questions on this? Yes.
Is that the same thing as just like controlling for education?
Yes, yes. So people use different words. So like conditioning on, controlling for, holding constant, they all mean the same thing. I'd say in psych, you probably hear controlling for most often. Political science, they love to say conditioning on. Economics, holding constant. Like, it's just weird. We always have 3 different ways to say the same thing. Statistics. Okay. So you can estimate the adjusted means. I wouldn't even worry about this. This is a weird thing. This is literally kind of just saying, imagining a world in which there were no differences in education and no differences in income, what would the average prestige differences be between these groups? You can kind of, it's quite a weird thing to do. So this difference between BC and WC here, the difference between 47 and 45, is the slope on WC in this model, negative 1.43. So it's kind of, but it's a weird thing to do. Like, it's a weird thing to think about the mean of something in an imaginary world where it's not, it has different levels of income and education than it actually does. Maybe useful in some circumstances, but I don't think you see it again in this course. You may never see it again in your life. So objects is just a useful command for understanding what is in a model object. And I guess here we're demonstrating that there's objects within objects. So one of the objects in this created model object is called model. And the model, you might have seen this in 101, it's actually just a data set with specifically just the data that we used in the model. And that actually is useful to note because that's going to come in handy in a lot of your exercises, because the nice thing about the model object is that it excludes any case that was not used in the model. It excludes any case with missing values, which makes a lot of things work a lot more smoothly, right? So like your n, for example, would just be the n row of this model object, 98, whereas, you know, the n row of the data set is like 102, I believe. Yeah, so like you can see like right there, to get the correct n to use in those formulas for covariance and stuff like that, I would prefer to use n row on the model, which is just the data that was used in the model. Anyway, we can now fit the fitted values versus the actual values. We're getting them from the model structure because of missing. Okay, so we're getting into exercise 2 now, which I didn't get to spend enough time on in the previous section, so I'm going to do it now. I need to give the plot more room. So what this is doing is it's plotting the fitted values from the model against the true values. So it's kind of the first plot that we saw, except it's dividing up by group. So blue collar, you can see that predicted prestige is lower, true prestige is lower. White color, same deal. With prof, you've got higher predicted prestige and higher actual prestige. And it's sort of fitting a different slope as well for each different group. So we're going to sort of, exercise 2 involves recreating this graph, but doing something a bit weird with the model slopes and the model predictions. So exercise 2. Wait, what happened to exercise 1?
It was just adding a line.
Yeah. Where even is it? Exercise 1. Yeah, add a y equals x line. It's really easy. It's in the other tutorial video, but it's basically like you just go AB line 0, 1. AB line takes a intercept and a slope to fit a straight line. But yeah, it's easiest exercise you'll ever do. So yeah, that was when we plotted the predicted values against the, why is it doing that? Graphics off. The predicted values against the true values, and then AB line 0, 1 just fits this straight line through them, y equals x. Okay. So yeah, the exercise 2 is a lot more convoluted. And what it asks us to do, on a separate figure plot, the predictions that one would have obtained for each group without taking the profession type into account. In other words, in the current model, each group has its own intercept. Replace that intercept by the average of the 3 intercepts. What do you see? Hint, I used a for loop through all the data. Like, okay, right. So, this is a very strange exercise. And it's not something that you're ever going to do again. It's literally just an exercise in R coding to get you to think about what a dummy variable really does to predictions. Because here, the way we're phrasing it is, adding the dummies gives the different groups different intercepts, right? And that's true, kind of. Really, what it does is it just gives each group a unique shift, up or down, right? Because each group is either the reference group, so they are just like the slopes on WC, the slopes on the dummies don't affect the reference group, right? So that's your kind of default slope. But for the other groups, whatever slope you fit, it just shifts it up or down for that group, because every single case is just 0 or 1 on those dummies. So they either get the boost or they don't get the boost or whatever. Like, so you can just think about it as just, you have these slopes we have these slopes on the continuous variables, and what the dummies do is just shift them up and down. And one way of thinking about that is, it gives these groups different intercepts. So what we're asking you to do, which is very strange, is to think about, well, what is the intercept for each of these groups? So we get 3, right? There's one for blue collar, one for white collar, one for prof. What's the average of those 3 numbers? And then take that average intercept and for every case in the data, make a new prediction using that average intercept instead of their group-specific intercept. It's a weird thing to do, and you'll never do it again, nor should you. But it's exercise 2, so we have to do it. So does anybody remember how we get the model coefficients? So we've fit the model, I believe. I think it's prestige.mod.1. How do we get these values in a vector? Does anybody remember? What's that? We used cbind, but there was an earlier step where we grabbed the coefficients out of the model. Yes, great. So we apply the function coef, and I'm just going to call it my coefs. Okay, so the intercept for the reference group, we know just from looking at this, right? What is that going to be? For the reference group, the intercept for the blue colors. So okay, so put it this way. If education is 0 and income is 0, and I'm in the blue collar group, what's the prediction this model makes?
Would it be the mean?
The mean? No. Just the intercept. Exactly, right? Because think about what I score. So I told you education 0 and income 0, and I told you I'm in the blue collar group. So you know that I'm 0 on the WC dummy and I'm 0 on the prof dummy. So this model, A plus nothing plus nothing plus nothing plus nothing, right? It's just A. It's just the intercept. So my prediction for the blue collar group, or the blue collar slope, and we can say BC underscore slope, is just my coefs, and I can use indexing, and I can either say 1, or I can actually name it inside the square brackets. So that's going to give us just the intercept, and that's the blue collar slope. Okay, so same question, but for white collars. Oh, sorry, I should say intercept. BC intercept, sorry. So what would the white collar intercept be if these are my coefficients? So again, we're imagining education 0, log 2 income 0, but we're imagining I'm in the white collar group. What would the prediction be? Yes. Does everybody see why? So again, this is the prediction model. My x variables, I mean they're all x variables, but here, like for convenience, we're thinking of education being 0, income being 0, but I'm in the white collar group, so I'm 1 on the white collar dummy. So my prediction is A plus nothing plus 1 times the white collar value, the slope, so negative 1.439, plus nothing, because I'm nothing on the prof. So we can just go BC intercept plus my coefs, and then just say type white collar. And that should give us a white collar intercept. Great. And now the same for the prof intercept. Except it's just type prof. So yeah, you can think about this as giving the three groups different intercepts, which literally in this case just means we make a different prediction for each group when these other variables are 0. I mean, we also make a different prediction for each group no matter what the values of the other variables are. And those predictions just jump up and down based on these slopes on the dummies. But you can think of it as giving them different intercepts. So now we want to get the mean of these three intercepts. So how do we do that? Oops. Is this one of those situations where I ask something too easy and nobody wants to answer it? Or is it the mean function? Yes. But then what? Because I actually don't think this is that easy. What else do I do here? C, yeah. So we do need a function within a function. So it's not that easy. And then, yeah, we're just going to put our three values. If I had my time again, I'd give them shorter names, but you know. So our mean intercept is negative 79.43137. So now we need to do the weird part, which is take that average intercept and make new predictions for each case. And what I'm actually going to do here is just create a new object called newpreds, and just compute it manually. So I'm not going to use a for loop like Frederick suggested, which you can do, but you don't really have to. It's just going to be this mean intercept plus, I'm going to use the model object. And so what I need to do is the mean intercept plus all the scores on education times the education slope plus all the scores on income times the income slope. Pretty easy, right? So this is going to be, well, first let me get the correct slopes. So I'm going to go plus my coefs, I guess it was called education, multiplied by, and then I'm going to get the education values from the model object. And then do the same thing for income. So it's log 2 income. And because this variable is weird because it's got the parenthesis in the name, you'll see something weird happen here. If I do this $, I can choose it, but what happens is it gets put in these quotation marks. Don't worry too much about that. Essentially, yeah, I think it probably just would not work if we didn't have them, because this is an R command, like let's see what it gives us. Yeah, attempt to apply non-function. So in this case, we kind of need those. That's not it. Literally, yeah, the easiest way to do it is just hit that $, and you'll see you can select where that actually is on the keyboard. I'm not actually totally sure. Anyway, so what this is doing, and I hope you sort of understand what it's doing, and I hope you also see like how weird this kind of is it's like we've got these slopes from this model, and we were just giving each group a boost or a detraction. Now we're not. We're just sort of saying, okay, every group you just get one intercept, the average of those three group intercepts, and but we're still making predictions based on your education and your income with the slopes from our model, which is like 3.28, and then income is like 7.26. But yeah, you don't get your own intercepts anymore. You all have to share a single intercept. So I've got the newpreds, and these are my new predictive values. And exercise 2, what it asks us to do is just create a new plot. So we can literally just steal this code, put it down here, but instead of the fitted values, we put newpred. And if we run this again, we should see a new model. And what do you notice? So like if this is every group having the same intercept, and if I go back through my plots, it's not there anymore. I guess I turned graphics off. Yeah. So this was every group having different intercepts, and yeah, I mean, I think the exercise asks us like, what do you see? So what do you see? So yeah, this is when we were allowing those group-specific intercepts, and then this is when we've taken them out. What is the difference between those plots to you? There's not that much difference, right? If anything, the predicted values for the different groups just get a bit closer together. So that you can just say that. Okay. So that's exercise 2. Are we running out of time? Okay. That's exercise 2. Even in the previous tutorial, I didn't get too much into exercise 3. It's quite easy though. But I might, well, I might just keep going now and do exercise 3, and then it'll be part of the second video. So if you have to go, you can go. Or if you don't have to go, you can still go. Or if you want to stay, you can stay. But this is my office hours, so I'm going to take up like 5-10 minutes of my office hours doing exercise 3. But I do think it's quite easy. Ham, is that a question? Yes, absolutely. Yeah, this is exercise 2 done, except you would need to write something about what do you see. So I'm going to move on because this will all be on YouTube. So I know those videos are not super high res, but you can make out the code, right, if you watch them. So, all right. Yeah. So that was just directly copied from above, and that's just specifying what determines the different colors in the plot. Okay. So yeah, now we're going to get into interactions, and yeah, like interactions are a big topic, and we're going to do a lot more on them. I think it takes a while to get your head around interactions and really develop strong intuitions about them. But essentially, the scatter plot matrix, this is kind of just what we did before, and you can kind of look at this and see maybe there's some interactions going on, right? So we can see, for example, that there's it's kind of like what looks like sort of a different slope for the relationship between prestige and women depending on type, maybe. Hard to tell really from this plot, but that's one thing we might look for. So we can compare the model that predicts prestige with income and education as additive predictive variables with a model that also includes a multiplicative term. So here what we're doing is prestige.mod.1 fits a model predicting prestige from education and income, and prestige.mod.2 fits a model predicting prestige from income and education and also an interaction term. And do you guys remember from 101 what an interaction term is, like how you actually get it?
Like there's a difference between the two independent variables. So we see a difference in the DV based on the two IDs.
Yeah. Although that sentence technically would apply to a model without an interaction as well. I mean, the key thing conceptually with an interaction, which is what I think you're trying to say, is that the effects of the variables depend on each other in an interaction model. So adding an interaction allows the effect of income to be different depending on education level. And at the same time, it allows the effect of education to be different depending on the income level. So you might see a situation where, and you do see actually in this data, at higher levels of education, there's a weaker relationship between income and prestige. Which, let's actually visualize that. So this code here, you're actually going to use, reuse this code for exercise 3 to visualize a different interaction. So the library effects makes this kind of nice plot. And I do like these plots. I think a lot of the time when you have interactions in your data, it's hard to really understand them until you plot them, until you actually like look at them in a graph. So what this plot shows us is basically 5 different versions of the relationship between income and prestige. And what these 5 different versions, the difference between them is the education level that we're talking about. So essentially what our model has done is, like I said, it's allowed the relationship between income and prestige to vary depending on education level. And so if you look at the top of these plots, you can see we go from education equals 16, so an average of 16 years education for that job, to education equals 6.4, an average years of education for that job of 6.4 years. And so what do you notice happens to the relationship between income and prestige as education goes from 16 to 6.4? Exactly. It's stronger. There's a steeper slope, right? So income is more strongly related to prestige at low education levels. Can you guys think why might that be? So this plot kind of shows us a bit of an interaction, right? Where the effect of income on prestige, or the relationship between income and prestige, looks like it's different depending on how high education is. When education is high, so when professions have more education, there's less of a strong relationship between income and prestige. When education is lower, so these are like professions where education is typically lower, there looks like to be a stronger relationship between income and prestige.
What's prestige again?
Prestige is just kind of how highly respected in society a profession is. So like maybe like a high prestige profession might be like heart surgeon or something. Like and a low.
Education would be the average education level in that field.
Yes.
Yeah, I think probably one explanation would be education would explain the prestige in the high. Well, if you have high education, which we will already have like relatively high prestige for that job, regardless of whether you earn a lot of money. For example, professors are poor, PhD students are poor. However, they have high prestige. We think that you're contributing to yourself for science, and yet in low education level, pretty much the more money you make, we think you're going for it.
Brilliant. Great job.
And that's what
Great job. Great interpretation. See what I'm saying? Like at very high levels of education, we may give jobs prestige in society even if they're not making that much money. Like an adjunct professor, right, at Berkeley, maybe they're just making as much money as like a garbage man, like maybe less, right? But society may tend to give them more prestige because of the level of education that they had to get to become an adjunct professor, right? So yeah, like there's a good reason why at very high education levels, maybe the relationship between income and prestige is not as strong. Yeah, really great job thinking that through. And this is the thing with interactions. Like interactions make you think, why would this relationship between these two variables depend on this other variable? And we think about interactions a lot in psychology. Great job. Library splines. This is like another thing that you're probably not going to see again, so let's not worry about it too much. Let's display the effect. This is kind of another way of modeling a nonlinear relationship between income and prestige. I'm not going to worry about it too much. We're going to do another ANACOVA. So this model matrix command is kind of cool because it shows you what interaction terms are. So for example, here's our data set, and here's our dummy variables, and we made these on the board earlier. And here's our values for education. And here, literally, is what the interaction terms are. It's the dummies multiplied by the education scores. So you can see the type WC by education interaction term is literally 0 if you're 0 on WC. And it's literally just your education score if you're 1 on WC. So interaction terms literally just are other variables multiplied by each other. But just mathematically, when you put those in the model, what you allow the model to do is to model effects where the effect of one variable depends on the level of another variable. And it's quite clever, actually. So essentially, we fit Prestige Mod 4a, which is a whole nother model. And we're now adding interactions between education and type and log2 income and type. And so we get this summary. So now we've got a bunch of coefficients, right? We've got an intercept, we've got a slope on education, slope on white collar, slope on prof, slope on income. But then we have interaction terms. So we've got a slope on the interaction between education and white collar, slope on the interaction between education and type prof, and likewise with logged income. And so in a very similar way to how WC and type prof provide sort of adjustments to intercepts, right? Remember, like they were doing, because everybody's 0 or 1 on those things, what they're doing is they're pushing up or pushing down predictions based on your group. What these interaction terms are doing is they're allowing for adjustments of slopes based on what group you're in, right? So a good way to think this through is like, well, what is the slope on education for somebody in the blue-collar group? Now, we know that if you're in the blue-collar group, you're the reference group, so you're 0 on all the dummies, right? So if education changes for somebody in the blue-collar group, so education goes up 1 unit, our prediction goes up 2.3357, right? Because these other slopes don't matter. Because all these other slopes have been multiplied by these dummy variables. And the blue-collar group are 0 on those dummy variables. So these slopes here don't matter at all for the blue-collar group. Their effect of education is just this guy, right? But think about this. What is the effect of education if I'm in the white-collar group? So now, if I'm in the white-collar group and my education goes up 1 point, what happens to the prediction? It's going to go up by 2.3357 because education has gone up by 1. However, because I'm in the white-collar group, I also get this, right? So I'm 1 on this dummy. So my prediction actually goes up by not just by 2.3357, but it also goes up by 3.64, right? So for every 1 unit increase, if I'm in the white-collar group, my predicted prestige goes up not just by 2.3357, it goes up by this plus this. Because, yeah, when I was blue-collar, I was 0 on this slope, right? I was 0 on this dummy. So my interaction term was also equal to 0. But if I'm in the white-collar group, so this is why you can think of these as creating different slopes. And one thing the professor likes to say is different slopes for different folks. So this would show us that, hey, if I'm in the white collar group, actually my slope on education is closer to 6, right? Because every time my education goes up by 1 unit, my prediction goes up by about 6 units. Different slopes for different folks. These guys adjust intercepts based on group. These guys adjust slopes based on groups. And we'll come back to this and we'll spend more time on this. And it definitely takes some time to get your head around. But yeah, this is key. And it's all about just understanding that whatever comes out in these summaries, all it's telling us is our model predicts that the value of the outcome variable is the slope plus this times the scores on this, plus this times the scores on this, plus this times the scores on this. Interaction terms are just adding new variables. And we're just adding slopes for those added new variables. So yeah, we'll deal with this more. But essentially, Model 4b is exactly the same. It's just another way of saying the same thing. So exercise 3, plot the result of this ANCOVA with interaction using the plot command and the effect command for education type in Model 4a. Try also the leverage plots and residual plots. Explain what you see. So plot the result of this ANCOVA using the plot command here. Okay, so it wants us to do this. Plot this. And like I said, that's going to give us these 4 different plots. The hints document tells you how to really interpret those plots. So go to the hints document and kind of give you some idea what those plots are telling you and just run them, interpret it. The effect command is going to be a bit more complex, and I'm going to let you figure this out yourself. But essentially, like, your first step will just be grab this code, put it there, and now you're going to change the model, obviously. The model is going to be different, and also you're going to have to change what's written in which interaction you want to visualize. So it might take some trial and error. I think the order you put the variables in matters in this command. So yeah, you're going to change the model, plot the interaction. You're going to plot, does it tell you which? Yeah, it tells you you want to be visualizing the education by type interaction in Model 4a. So that kind of tells you really what you have to do. But also I want you to interpret it. So like write something. Write what you see when you've got the right model. And then also try leverage plots and residual plots. And like I said, the information for those guys is just going to be in the hints document. Figure margin's too large. So you're going to run that, have a look at it, tell me what you see, try to interpret it based on the hints document and the residual plots and like what you know. And I did spend more time on these guys in the other section. So watch that video. I'm going to post both videos, like a 2-part. Yeah, and I mean, yeah, there's a lot in this tutorial. So I think it was worth spending extra time focusing on things in a bit more depth. Could not find function. Oh, yeah, right. So there's a typo. It's actually residual plots. So don't get fooled. Yeah, that's what you want to be looking at. Okay, that's it. I'm going to stop this video, and now official office hours can start.